Hello, welcome again. We are covering the topic centrifugal compressor for civil services mains, IFS and gate aerospace. And next subtopic in this main topic of centrifugal compressor is compressor characteristics. So in the last topic we studied some non-dimensional quantities for floating compressor characteristics. These were first was pressure ratio, second was temperature ratio, and this is uh, non-dimensional mass flow rate. Okay, and here R is a constant quantity, D is a constant quantity, so we omitted these. So it becomes m root T naught 1 by P naught 1. Although it is not non-dimensional, but it is derived from a non-dimensional quantity, that is this quantity. So it is called non-dimensional mass flow rate. Similarly, this is your non-dimensional speed. Here d is constant, r is your constant, so we are omitting this, so it will be n by root t naught, t naught 1. Okay, so this is called non-dimensional speed. However, it is also not non-dimensional, but if we multiply it by d and divided by root r, then it will become non-dimensional. So these are the four non-dimensional quantities for floating compressor characteristics. So by these, first we will plot the graph between pressure ratio and non-dimensional mass flow rate for different value of non-dimensional speeds. Okay, then we'll draw the graph between temperature ratio and non-dimensional mass flow rate for different value of non-dimensional speed. And then using this relationship, efficiency, that is T02 dash minus T01 divided by T02 by minus T01. So we will or using this isentropic relationship, then we will have the relationship between efficiency, pressure ratio and temperature ratio. Okay. So then by these two diagrams we can plot the graph, and from this relation we can plot the graph between efficiency and non-dimensional mass flow rate for different value of speed. Okay. So this we will do, and I will just read out first page for you. First point is the value of the dimensional analysis is now evident. Okay. We have pressure ratio, we have temperature ratio, we have non-dimensional mass flow rate, we have non-dimensional speed. It is only necessary to plot two sets of curves in order to describe the performance of a compressor completely. Second point, the stagnation pressure and temperature ratio are plotted separately against non-dimensional mass flow in the flow of a family of curves, each curve being drawn for fixed value of non-dimensional rotation. So here we have taken pressure ratio and here non-dimensional mass flow rate, and will plot the graph for different values of non-dimensional speed. And here we will take temperature ratio and here non-dimensional mass flow rate, and will plot the value or plot the graph for different value of non-dimensional speed. From these two sets of curves, it is possible to construct constant speed curve for isentropic efficiency plotted against non-dimensional mass flow rate, because efficiency is given by this relationship. Efficiency is T02 dash minus T01 divided by T02 minus T01. Further it can be written as P02 by P01 base for gamma minus 1 by gamma minus 1 divided by T02 by T01 minus 1. Okay, so then we have a relationship between efficiency and mass flow rate for different value of non-dimensional speed. Then we can draw this up. Now let us draw the first characteristic, that is between pressure ratio and non-dimensional mass flow rate for different value of speed. Suppose we have a particular speed, for one speed we are drawing the graph, and this is the compressor, this is impeller, this is diffuser, and this is a downstream of compressor, and these outlet of compressor and downstream of compressor is connected by this valve. So initially the valve is shut down, okay, so that no air is flowing from outlet of compressor to down. Yet there will be some pressure buildup, that is due to the movement or rotation of impeller. The air trapped in between the impeller will get pressurized, so there will be some pressure building in the impeller when the even when the valve is shut down. Okay. So, but there will be no increase in pressure in the diffuser part. The increase in pressure will be in the impeller part only, because it will not um, contribute its quota, because the air valve is shut down. The pressure rise will take place due to the impeller movement only. So here, when the valve is shut down, there is no mass flow rate. This point represents the point corresponding to no mass flow rate. So this pressure ratio will build up due to impeller movement. So when we start opening the valve, this valve, and a small mass of air enters through this valve, then diffuser will also contribute its quota. It will also increase its pressure. Okay. So when there is some mass flow rate, the pressure will start rising like this, or pressure ratio will be more, and it will go on increasing up to point B, where the efficiency is maximum. Okay. So at point B, the pressure ratio will be highest. Once it reaches at the point B, by opening the valve and increasing the mass flow, after that it will start falling. Okay. because because at point B the air angle will be different from the vane angle, and mass flow rate will be more, and air will not follow the impeller vane. So pressure rise is not pressure rise do not increase after point B. It starts decreasing. Okay. And as we go on increasing mass flow rate, then the pressure start decreasing in this way. Okay. And finally it becomes equal to 1 at point C. So this is for a particular speed, that is n root T0y, known method. So I will read this out. Before describing a typical set of characteristics, it will be as well to consider what might be expected to occur when valve is placed in delivery line of the compressor running at constant speed is slowly open. So this is your valve, and this is your delivery, and this is your downstream of compressor. When the valve is shut and the mass flow rate is 0, the pressure ratio will have some value corresponding to centrifugal pressure head by the action of impeller on the air trapped in the vane. It is important to note that there will be no pressure rise in diffuser, as there is no flow. Okay. As the valve is opened and flow commences, the diffuser begins to contribute its quota of pressure rise, and the pressure ratio improves. At some point B, where efficiency approaches the maximum value, the pressure ratio reaches a maximum. So here, okay. Here, and then any further increase in mass flow will result in a fall of pressure ratio. For mass flow greatly in excess of that corresponding to design mass flow, the air angle will be widely different from the vane angle. Break away of air will occur, and efficiency will fall off rapidly. In this hypothetical case, the pressure ratio drops to unity at C when the valve is fully opened and all power is absorbed in overcoming the internal frictional resistance. The above curve ABC is for a particular rotational speed and divided by root T01. So family of curve can be generated for different values of n root T0.